Hello. So, hi, my name is Jason Stanek. I'm going to start my talk now. Before we begin, I'd like to say that it's an honor to present to you today. SecDSM is an amazing organization with fun events, informative talks, and talented participants and cybersecurity professionals such as yourselves. And that Des Moines and Iowa more generally is lucky to have SecDSM. Last year, I spoke to you about the risks that quantum computing poses to cyber assurance and our prosperity and what we can do about it. I spoke about how confidentiality of today's industrial secrets can be circumvented now through record now, decrypt later attacks. And I spoke about how the availability and integrity of our critical infrastructure could be at risk if or when quantum computing becomes a reality. So I hope that a quantum-resistant layer of encryption is at least on the radar for enhancing existing encryption. Today I'll talk to you, though, about a growing concern at the intersection of human health and cybersecurity. So to outline the talk, I'll share a little bit about myself, bring out some concerning trends, give a crash 101 in genetics, and talk through some of the challenges that may be ahead that you may be able to help mitigate. So my hometown is here in Des Moines. As you know, Iowa is known for being the insurance capital of the United States and the headquarters of the World Food Prize. But Iowa is also where the electronic digital computer was invented, up at Iowa State, called the Atanasoff-Berry computer by John Vincent Atanasoff and Clifford Berry, which is one of the reasons I chose to attend Iowa State. I also, at Iowa State, chose to do 2 different degrees simultaneously. I did a degree in computer science and in finance, and later went on to do a PhD in computer engineering. After my PhD, I went to work at DuPont Pioneer as a research scientist, working on computer-assisted breeding. I did a number of things there, from digital automation, data pipelines, and machine learning, and built tools to bring out insights for breeders and management. After about 5 years at DuPont Pioneer, I went on to work at a company called Scientific Games. The focus of my work there was on special projects like experience personalization and improving returns on customer acquisitions. I stayed at Scientific Games for about 2 years before getting back into the biotech space at Bayer, working on a wide variety of projects. I teamed to build platforms for data ops and ML ops, and put together and was a part of a number of data science collaborations. I also led mentoring program, got involved in a number of other activities. And along the way, I also did a master's in business administration from the University of Iowa, and served as an associate director on the board of directors for Greater Iowa Credit Union. Most recently, I've developed some patent pending technologies for my company, Mendogene LLC, for the design of superior gene therapies and for seed genetics. Now, a little bit about me personally. So here's a picture of me and my family. My wife Kimberly is next to me. She is a registered dietitian, works for the state. My daughter Ellie, she's in 6th grade, and she's already exceeding the standards of her grade. She plays piano and has a respectable butterfly stroke in swimming. My other daughter Sophie, she's in 9th grade, but is 2 years ahead in math. She also runs cross country to show choir, and in 7th grade, she was on a team in mock trial that ranked 11th out of more than 150 teams in the state. Both girls are avid readers and do gymnastics, and play ukulele. All right, a little bit more about my sphere. So some interesting things here. My mother was the first woman to get a master's degree in computer science from Iowa State. My dad has a PhD in physics and invented Powerball. My brother has a PhD in computer science, and after building a streaming platform that was bought out by Amazon, he now works for Discord. Interestingly, my brother and his schoolmate, Feng Zheng, also from Des Moines, you may know his name from, or as the inventor of CRISPR gene editing, and he's also the co-founder of a number of companies, one of them called Pairwise. So each of them, both of them, were bestowed the key to the city of Des Moines in the same town hall meeting for their respective science and computing competitions. And then, interestingly, another one of my brother's schoolmates was Ben Silberman, the founder of Pinterest. Okay, so let's talk about trends. So about 10 years ago, the FBI director at the time said that there had been two types of large companies in the United States. Large companies that have been hacked, and large companies that didn't know that they've been hacked. If you fast forward a few years from there, you have a national adversary pulling off a hardware intrusion, some call the holy grail of hacking, by hiding a backdoor in chips in circuit boards that are said to have ended up in servers at Amazon and at Apple. So last year, I pointed out this concerning trend in cybercrime, or at least reported cybercrime, which was reported in 2023 to have been $12.5 billion. A year later, with another year having gone on, reported cybercrime damages have risen to approximately $16 billion last year. But reported cybercrime is only the tip of the iceberg. A lot of cybercrime doesn't go reported. In fact, 80% of cybercrime is unreported. And more intrusions may not be known. And in 2016, the theft of intellectual property by foreign adversaries was said to have been an annual cost to the United States of about $500 billion. So to put that in perspective, that's about the equivalent of the entire spending of of Americans on pharmaceuticals in a year. In other words, it looks like we're losing what is equivalent to an entire industry each year. So a question I would ask you is, are we losing this cyber assurance battle? And it kind of looks like we are. Today, we have problems in cyber assurance. With each one of us in cyber assurance, there are about 50 or more adversaries trying to break the door down, and they only have to be right one time, whereas we have to be right every time. And sometimes information security gets relegated to patching, but there's so much more to information security. There's confidentiality, availability, and integrity, which are all important. And we need to keep in mind that it's not just digital data that we're protecting. A year ago, we saw a preview via the CrowdStrike incident that impacted the availability of airlines, emergency services, government services, and more. And a couple weeks ago, we saw AWS go offline for a day. Imagine what could have happened if those had been intentional and coordinated. And there is evidence of intention of using the digital world to attack the physical world. And there is evidence that no target is off the list. To illustrate the point, there's a small water treatment plant in Littleton, Massachusetts, that serves a community of only about 10,000 people, so much larger than where we live. And recently it was discovered that a foreign nation had hacked deep into that water treatment plant. So why do we care, and what does this mean? Well, according to Tim Haw, who is retired NSA, retired 4-star general, I'll quote him here. So if you're willing to go after a small water provider in Littleton, Massachusetts, what other target is off the list? Because if they're willing to go after that small provider that doesn't have a national security concern or connection, that means that every target is on the list. The only value would be for use in a crisis or conflict, end quote. And with water treatment plants, the energy grid, refineries, navigation systems, cars, automation of agriculture, like gene edits and pollinations, that feed into the food supply chain here at home, or manufacturing of over-the-counter prescription medicines being networked and and connected to the cloud, the physical world has become integrated with the digital world as cyber-physical systems, where the physical world depends on digital connectivity, meaning the physical world depends on cybersecurity. So let's think about what's at risk if we continue on the same path we are on. Let's think about the availability of what we take for granted. The availability of things like money and banking, airlines, 911 and other emergency services. Let's think about the confidentiality of technologies that assure our competitive advantages in the world. Trade secrets in high-tech industries like material science, biotechnologies, medicine, agriculture, semiconductor manufacturing. And it's not just about availability and confidentiality anymore. It's about the integrity of critical infrastructure. Critical infrastructure and supply chains, utilities, water, communications, electricity, hospitals, medications, food. Let's think about our way of life, because our prosperity is not a given. Our prosperity depends on confidentiality, availability, and integrity. And our way of life depends on you. So I'll be sharing a bit about the risks to integrity of the food supply and medicinal manufacturing, which I believe are in critical need, folks, cybersecurity folks like yourselves, who can shore up vulnerabilities that most people will either miss or dismiss. To start, I think it's helpful to provide a little background in genetics and how it's related to something you may be more familiar with, which is software. So you all know that DNA contains genes, which are sometimes called the source code for life, and different genomes code for different people, animals, plants, and other organisms. Some genomes are even used to develop medicines. And within each organism's genome, there are tens of thousands of genes or variants thereof. And those tens of thousands of genes lead to production of tens of thousands of different types of proteins that interact with each other and facilitate chemistry. The types, quantities, and placement of these proteins define each cell type, and the diversity of cells work together to support life. Now, each gene codes for at least one protein, and there's many, as I mentioned, many types of proteins, and proteins can work alone or fit together and assemble into protein complexes, which may further perform some kind of function. And if we think of enzymatic proteins and complexes as software functions that process data, then the chemicals and biochemicals called metabolites are the data that the different functions process and transform into other data or metabolites. Collectively, a set of enzymatic proteins or functions present in a cell define what the cell can do and the metabolites available to it, or to the metabolites available to it. And which proteins are available in the cell depend on the presence and fluctuation of different biomolecules, including biomolecules called transcription factors, which are also proteins, or at least some of which are also proteins. So transcription factors work like conditions within an if statement of a gene, where each gene may be conditioned upon different sets of transcription factors, and when the set of conditions of that if statement of a gene are satisfied, then the gene is unlocked for the production of the specific protein that it produces. And the set of transcription factors for a gene can be singular, plural, or even empty. That is, some genes may be conditioned to depend on compound logic, single condition, or always be on. And different genes can be conditioned on the same transcription factors. In other words, one or more transcription factors can kick off and maintain different processes. And collectively, the set of processes in a cell define that type of cell or program that operates on the metabolites or data available to it. Now, genetics is kind of finicky, kind of like software is. Just as there's different causes of bugs in software, there's also different causes of bugs in genes. For example, if you're familiar with C or C++ or null-terminated strings, genes are a lot like fragile null-terminated strings. A null-terminated string, just for giggles here, I'll define it. It's a sequence of characters whose end is indicated by a specific value called a null. Usually the value is 0. And in genes, instead of characters in a string, the gene is described as a string of what are called codons. And each codon either describes a character in a protein string or what is referred to as a stop codon, which indicates the end of that protein string. And just like properly placed null termination in a string in software can prevent buffer overflows and ensure the intended program operation, a well-placed null termination in a string in biotechnology can be used to create produce or other crops that are healthier or have other intended benefits. But as you know, an unfinished function in software can be catastrophic. So too can premature null termination of a gene, both to our health, for example, as in the case of a single nucleotide polymorphism, being able to cause muscular dystrophy, and also to our food supply, where gene differences could cause crop susceptibility to disease, for example, by allowing the growth of carcinogenic or poison fungus or bacteria that's harmful to humans or animals. And as you can imagine, where a protein is null terminated is not the only type of influencer that can help or hurt agriculture and human health. Other types of gene mutations, extra genes, or missing genes can also improve or hurt outcomes. So let's talk about crops we grow for food and the medicines we use for health, and a couple potential problems that are visible. Generally speaking, in the biotech field, developing a better product, such as a more productive crop or a more effective medicine, is done by screening a diversity of genomes or a diversity of substances for some observable improvement or effect, to find the so-called needle in a haystack. And these genomes and substances are either generated, for example, by breeding or by gene editing, or collected from all over the world. Then a product development pipeline is used to narrow down this candidate genomes, the candidates of genomes and substances. And here's an illustration of a typical product development pipeline. On the horizontal, there's different stages of the pipeline. And the width of the openings of the funnels indicate the number of candidates for which consideration or that are being considered or selected at each stage. The intention of the pipeline is to allow for the comparison or ranking of the generated and collected genomes and substances, and multiple stages are used because of noise and comparative measurements. So even though the screening might not reveal the top products in the end, the pipeline's designed to statistically increase the chances of doing so. However, there is or are potential security problems with this approach. Can anyone think of a security problem? So one potential problem is the collection process. So would you put a USB stick that you found in a parking lot into your computer? No, I hope not. So Similarly, would we put a genome, or should we put a genome that we found in a field into our food or medicine development pipeline? Do we know what genomes were used, and is the chain of custody or generation and transformation known? Second problem is that the coupling of the cyber world with the physical world. If something published by someone else halfway around the world is used to build and impact an AI model that's used to develop crops, used in food, or to develop medicines, can you confidently say that that model will not hurt someone who ingests the food or is administered the medicine? Is there transparency into what or who influenced the model and what it reports? And third, if an opportunistic hacker can get into your digital systems to steal your trade secrets or ransomware your data, do you think that a malicious and well-funded hacker could alter a gene edit or outcome? So I hope I've convinced you that the integrity of our data and systems are incredibly important, especially when they control critical infrastructure that helps design our food and medicines. Especially in the age of AI, deepfakes, and misinformation, where we may not be able to trust what's produced outside of our organization, and in the age of pervasive hacking and intrusions, where we may not be able to even trust what's produced inside of our own organization. And with the growing dependency of physical systems on digital systems, such as that water treatment plant in Littleton, Massachusetts, and with the increasingly powerful biotechnologies, such as those used to improve agricultural genetics and design better medicines, cybersecurity and data integrity are indeed more crucial than ever. And there is something we can do so that we can all make better decisions. We can improve life with cybersecurity by stepping up our cyber defenses of our digital infrastructures to better detect and prevent intrusions, by including cybersecurity as part of a reproducible engineering design process as opposed to an afterthought, so that when we spin up digital infrastructure, it's secure from the start as opposed to doing a half-assed remediation later. So we can also build better data systems that facilitate traceability and reproducibility. We can step up our capabilities that assess bio-based and other products for safety, and by detecting biological, chemical, and other non-digital intrusion threats. And we can eliminate or reduce dependency of such critical integrity assuring systems on public cloud infrastructure, so that we have greater assurance that our adversaries can't deny us our own services, or steal our trade secrets, or corrupt our supply chains. Finally, I should mention that my company, Managene LLC, has a patent pending with over 250 claims that does not require AI to improve crops or design gene therapies. It doesn't depend on screening genomes found in a field somewhere. It can help design better foods and more successful gene therapies, and can help ascertain the safety of some gene therapy designs offline, and more, so that our prosperity depends less on chance and the hope that our adversaries play nice, and instead we assure our collective prosperity by working together across disciplines and empowering the best talents with the best technologies. Because I do not think that we can improve life without cybersecurity. Lastly, take this opportunity to thank SecDSM and today's sponsor, Abnormal Security, for helping make events like these possible. Thanks very much for the opportunity to talk today. I hope you found my talk helpful. And one more thing, I should mention that one of the best ways to show your appreciation is to please consider giving back to the SecDSM community. For example, by proposing a talk of your own to share your own experiences or know-how. Here's a QR code if you'd like to submit a SecDSM talk. Questions? Thank you very much.